Silver is the best conductor of electricity in the world, outperforming both copper and gold. Every year, over 25,000 tons of silver are mined globally, but instead of ending up in jewelry stores, most of it powers the modern world in microchips, solar panels, surgical tools, and more. But have you ever stopped to wonder how silver actually comes to life? Behind every milligram of silver lies a surprisingly complex and demanding industrial journey. From raw ore buried deep underground, silver goes through a meticulous series of steps: crushing, separation, chemical leaching, precipitation, electro-refining, and finally shaping into usable forms. In this video, we'll take you inside the modern silver-making process, from deep mines to high-tech smelters, from rough metal bars to the polished materials that drive our technology and touch everyday life. Silver is not just a metal, it's part of the long journey of human progress. Mined for over 6,000 years, silver was once used as currency, a symbol of religion, and today it has become an essential foundation of the modern electronics industry. Beyond its material value, silver is a silent warrior in the fight against bacteria. Studies show that silver ions can kill more than 650 types of bacteria and fungi, including drug-resistant strains. Even in tiny amounts, silver can break down cell membranes and stop microorganisms from multiplying. Thanks to its powerful antibacterial properties, silver is widely used in healthcare, from antiseptic dressings to surgical equipment. With the highest electrical conductivity and light reflectivity of any natural element, silver plays a central role in the world of technology. In electronics, it's used to create circuit boards, connect chips, and transmit signals at lightning speed. In renewable energy, it's an irreplaceable component in solar panels, where every electron must move with precision and efficiency. Silver mining. The extraction process begins by expanding underground tunnels, a network carved through bedrock using specialized rotary cutting drills. These machines are capable of penetrating hard rock with high precision, extending thousands of meters of tunnel every month. The drill head presses against the rock surface, spinning at high speed, gradually shaving away geological layers like a giant mechanical blade. A hydraulic system allows the drill arm to adjust its direction, lifting, lowering, or tilting to follow the terrain inside the mine. Despite operating in dark, damp, dust-filled conditions, the machine runs reliably thanks to laser guidance, sensors, and an automatic oil cooling system. Once exploratory drilling identifies ore-rich zones, workers bore holes and load them with industrial explosives. Each blast is carefully calibrated, strong enough to separate the ore from surrounding rock, yet controlled to preserve the integrity of the mine structure. The blasted rock is collected by heavy-duty trucks and transported via lifts or conveyor belts to the surface. Every step of the extraction process, from drilling and blasting to hauling, is monitored in real time from a central control room, where parameters like air pressure, drilling speed, and load weight are tracked continuously. Once transported to the surface, silver ore enters its first stage of processing, primary crushing. Visually, it looks no different from ordinary rocks. Silver ore processing: rough, heavy, and shapeless. But to extract the value hidden within, the entire mass must be standardized in size. This is where the jaw crusher comes into play. It consists of two high-strength manganese steel plates, one fixed, the other moving, functioning like a mechanical jaw that compresses the ore between their ridged surfaces. The crushing action breaks down the rock structure into smaller fragments. The deep grooves on the plates are specifically designed to control the breakage rate and prevent the formation of overly fine particles that could lead to valuable mineral loss. The system is operated almost entirely automatically. Integrated sensors continuously monitor rotational speed, crushing pressure, temperature, and load in real time. Each parameter directly impacts the quality of the output. If the pressure is too low, the rocks remain intact. If it's too high,
The ore may be overcrushed, resulting in unnecessary waste. At regular checkpoints, technicians measure the size of the crushed material. The goal is to maintain a range between 20 and 100 millimeters, small enough to further processing, but large enough to retain as much of the silver content as possible. After leaving the primary crushing station, the silver ore moves on to a more refined system, fine grinding. While the previous stage focused on breaking down rock structures to achieve uniform size, the goal now shifts entirely to transform solid material into ultra-fine powder ready for chemical extraction of precious metals. At the heart of this system is the ball mill, a massive horizontal steel cylinder filled with hundreds of hardened stainless steel balls. As the cylinder rotates at a controlled speed, the balls begin to move chaotically, colliding with each other and with the ore inside. These repeated impacts generate intense abrasive forces. No coarse fragments remain. What comes out is a fine powder with particles smaller than grains of sugar. Every parameter, from rotation speed and the ratio of balls to material to the precise amount of added water, is continuously monitored and adjusted by a central control system in real time. This ensures maximum grinding efficiency while also extending the lifespan of the equipment and minimizing the loss of valuable material. Once the ore reaches the desired level of fineness, the mixture is transferred to the flotation system, one of the most advanced mineral separation methods in modern metallurgy. Here, the slurry of mineral powder and water is directed into large agitation tanks. In the continuous swirling motion, a small amount of reagent, typically xanthate or a sulfur-based compound, is added to make the silver particles hydrophobic. At the same time, millions of microscopic air bubbles are injected from the bottom of the tank. The silver particles attached to the bubbles gradually rise to the surface and form a thick layer of mineral-rich froth. This froth is gently skimmed off and sent for further processing. Meanwhile, clay, rock debris, and non-reactive impurities sink to the bottom and are carried away through a separate flow. To maximize recovery efficiency, the system typically includes a series of interconnected flotation cells, which help recover residual silver from the froth and minimize losses to the greatest extent possible. At first glance, flotation may seem like nothing more than a bubbling tank, but in reality, it's where surface chemistry is precisely controlled, a process that has elevated metal separation to an entirely new level. After flotation, the resulting mixture is a silver-rich mineral slurry that still contains a significant amount of water. To remove the excess liquid, the slurry is directed into large settling tanks where gravity takes over from machinery. The heavier mineral particles gradually sink to the bottom, forming a thick sludge layer, while the clearer water rises to the top and is recovered for reuse. The geometry of the tank, the viscosity of the solution, and the inflow rate are all carefully calculated to ensure stable settling performance without clogging or overflow. The concentrated sludge at the bottom, now with a texture similar to thick cream, is pumped into temporary holding tanks ready for the next stage, preliminary smelting. Although it may seem simple, settling is the final natural concentration step, efficiently collecting silver-bearing particles without requiring any chemical intervention. After leaving the flotation system, the silver-rich froth is collected, thickened into a dense slurry, and transferred to the preliminary smelting stage, melting process, where fire and metal begin to interact. The entire batch is fed into a specialized furnace operating at temperatures above 1000 degrees Celsius. The furnace, shaped like a rounded crucible, is lined with high-temperature refractory materials capable of withstanding sudden fluctuations in heat and pressure. Once the lid is sealed, the mixture undergoes purification by fire. As the temperature gradually rises, the mineral layers begin to melt. More reactive metals, such as lead and zinc, oxidize and rise to the surface as slag. Silver, being denser and more stable, sinks to the bottom, forming a precious sediment-like layer. The entire process is monitored by thermal and pressure sensors. If the furnace is too cool, the silver won't fully separate. If overheated, there's a high risk of slag combustion and metal loss. While automated controls assist the operation, the skill of the furnace operator remains irreplaceable. Each smelting batch demands precision, experience, and the ability to judge the process.
Down to the degree because with fire, even a slight misstep can cost the very value hidden inside the ore. In bar form, silver appears complete, solid, heavy, and well-defined in shape. But inside, it still hasn't reached the level of purity demanded by modern industry. This is where refining takes over, a quieter process, but one that requires precision on an atomic scale. At the refining facility, the impure silver is melted again in a modern induction furnace. Both temperature and electrical current are tightly controlled. The entire operation runs in a closed-loop system equipped with recirculating cooling and sensors that continuously monitor current, voltage, and crystallization rate. All parameters are recorded and displayed in real time at the central control station. Under the influence of the electrical current, silver leaves the anode, dissolves into the solution, and gradually crystallizes onto the cathode, now pure, uniform, and free from unwanted elements. Metals such as copper, lead, and zinc settle at the bottom as anode sludge. After several hours of operation, a thick layer of refined silver forms on the cathode. It is carefully removed, trimmed, and weighed with precision instruments, accurate down to the gram. While still in liquid form, silver is poured into rectangular steel molds, each one prepared like a predefined slot, shaping its fate. This marks the beginning of the transformation from molten metal into solid form, typically reaching a purity level between 85% and 95%. The silver flows steadily and smoothly into the molds, its surface rippling like mercury beginning to set. Temperature control at this stage is critical to prevent thermal shock, cracking, or the formation of internal gas bubbles. The mold surfaces are coated with a layer of graphite-based release agent, allowing the silver to flow freely without sticking to the walls. Each raw silver bar typically weighs between 25 and 30 kilograms and still contains small amounts of other metals, such as copper, lead, or gold. This is the moment when silver takes on its definitive shape, no longer ore, no longer mineral slurry, but a solid metallic entity. Beneath a thin layer of metal dust, in the small workshop, bars of refined silver, seemingly complete, begin a new journey: jewelry making. Each silver bar is remelted in a small-scale furnace, typically fueled by charcoal or gas. The temperature is just high enough to return the metal to a molten state, while still allowing the artisan to work at close range. The shimmering silver is then poured into simple molds, rods, wires, or occasionally thin plates. These molds are not elaborate. Their purpose is purely functional, to create blanks, the rough foundation of a piece that will undergo many more transformations. From these blanks, the craftsman begins the shaping process. Silver sheets are thinned by hand-cranked rollers, passed through repeatedly like dough being flattened until the desired thickness is achieved. Wire is drawn through a series of copper dies with gradually smaller openings, like spinning thread, only with metal. For components like rings, bracelets, or pendants, the artisan begins to bend and shape, a process guided not strictly by measurements, but by a feel for tension and years of experience. Once the form is set, the piece moves into finishing, sanding, polishing, sometimes engraving or marking. Some items are polished to the point where they reflect the ceiling lights above. Others are treated in the opposite direction, textured, matte, made to feel like coarse fabric freshly woven. The final detail is often what the craftsman approaches most carefully: engraving names, setting stones, hand-carving patterns. Each cut is a commitment, irreversible, unrepeatable. Silver in this phase isn't shaped by complex machines, but by the steadiness of skilled hands. Every detail exists for a reason, not merely for beauty, and never just for show. The journey of silver is a blend of industrial technology and artisanal mastery, from anonymous mineral to refined bar, from conductive material to personalized jewelry.
Every step reflects the labor, technique, and respect devoted to this seemingly familiar metal. If you found this journey meaningful and want to discover more stories behind intricate manufacturing processes, leave a comment, share the video, and subscribe to the channel so you don't miss what's coming next. Thank you for watching until the end, and we hope that from now on, every piece of silver you hold carries more than just a metallic shine.